Okay, let's go through a few, actually two R examples for the logistic regression. One is the one that we used in our slides. Here I'm just showing you how did I get the results, and all the details are all included in our slides. So for this first one, it's simple for this default dataset. And those are the syntax and the results you saw on the slides. Well, the second example we're going to work through is about stock market data. So this data set have the percentage returns for the S&P 500 stock index over 1,250 days. From beginning of 2001 until the end of 2005. And for each date, we have recorded the percentage returns for each of the 5 previous trading days. We call it lag 1 through lag 5. And we also have recorded the volume. Let me see. This look better. Another variable we have is the volume, which is the number of shares traded on previous day, and it's in billions. And today is the percentage return on the date in question. So we have the percentage returns for 5 previous days and number of shares traded in previous day, we call it volume. And today is for the percentage return on the day in question. And direction is our response variable, which is whether the market goes up or down for today, like on this date. Well, this data set is also from this ISLR, from this work, Introduction to Statistical Learning with Applications in R. And by the way, that textbook is available online for free. Yeah, let's just do the regression stuff. Right? We attach the data here, and these are the names of the columns in the data set. And we try to take a look at the correlations among those variables, all these variables. But we removed the binary one because we cannot get a correlation for that one, right? So we remove that one, we take a look at all others correlation. Well, if this is not very clear for you, a better way is to do a map, a heat map, like this, with the colors indicating the value. With the deeper color means it's a higher number. Well, here we just use the absolute value of the correlations in this table, because either it's positive or negative correlations. If the absolute value is large, that means they are highly correlated, no matter it's positive or negative. Well, just by looking at this heat matrix, heat map, we can tell, well, on the diagonals, it's supposed to be 1, right? Because it's the correlation with itself. And this this orange one is the correlation between year and volume. So this is volume and this is year. So the correlation between those two is relatively higher. If you look at the table here, it's 0.54. So it's relatively higher compared to others. So it appeared to be a relatively darker color. And those lines are not really correlated. So while we find this year and volume have some correlation, let's make a plot. Like this is actually a time series plot because it's the volume versus the year, yeah, like the time. Yeah, we did a time series plot. Well, this just shows the daily changes. Well, it's a bit messy here, but if we want to just take a look at the graph trend, we can do a smoothing over the data points here. So I use this smooth function of this volume column. And this is after we smooth with art. It's slightly better compared to look at this one. It shows some upward trend, right? The volume of change as things go up. Oh, this better this example is picked from the SLR book, and following that book, we fit a model to predict the direction use this flag variables and the volume. And this is how you do it. You do this GRM and specify the family being binomial and do a summary of it. Well, actually, the work used this example, it may not necessarily be like really significant model or good model, but this is just for illustration purpose. Like how do you fit the model and how do you look through different things. And this is used as a summary, and corresponding p-values are not very promising, right? Because it shows maybe like none of them are really significant with this coefficients. And we can extract the coefficients here. This is how we do it. And we can also get the summary output, especially for the coefficients and the p-values. And we check how many of them are less than 0.05. Actually, none of them are less than 0.05 in this column. This is how you get that column. So this is the false column of this variable or this object. Sorry, this object. Well, I said this means it may not be a good model, but for illustration purpose, let's just keep on with it. And I'll show you how to do prediction. We can use this predict function, same as we used before, but in this case, we are predicting the probabilities that the market will go up given the value of predictors. So remember, in logistic regression, this straight line linear model is modeling the probability of y being 1. But in this case, y being 1 means the market go up. So y equal to 0 means market goes down. So this is how you do the prediction, and you specify type equal to response to get the probabilities corresponding to each of your, like this is for your first 10 observations, you get the probability. So I put a note here. This isn't give you the prediction of which class, like up and down, it's giving you the prediction probabilities. Because we ask for the type equal to response. And if you forget, like y equals to 1 means what, you can do this contrast with this direction variable. It will tell you like 1 means up and 0 means down. just do not confuse about this two things. Make sure you know what it means by the y equal to 1. And what if we want to get the predicted classes? At least the probability, I said you can like set up a probability cutoff. Like above 0.5, you say it's going up. Below 0.5, you say it's going down. So this is how we do it in R. And first of all, we do a vector of like everything in this vector. This is the length of this vector. We just repeat this string for this many times. So we get a whole vector of being down, and then you set some of them to be up. So basically, you change the value to up if this corresponding probability is greater than 0.5. So this is the probability that you got from this model fitting, and this grm.plot greater than 0.5. It gives you the index in this vector being greater than 0.5. So you just pick up those the corresponding index from this vector and set it to up. Well, once we do prediction, we kind of want to take a look at how accurate our prediction is. And so for this logistic regression or for like classifications, we can look at a confusion matrix and look for how to calculate the accuracy. So this is what a confusion matrix looks like. So you just do a table where on the row is the predicted value, and on the columns is the actual direction. So if you do a table of these two vectors, it will count how many of the predictions matched with you predicted down, and the actual direction is also down. It's here on this diagonal, and being predicted up, and the actual value being up, you have so many of them predicted correct. So this on the diagonal, it tells you how many cases you have predicted right, and those off diagonals is those you predicted down, but actually it's up. So this matrix is telling you how accurate or how much mistake you made by this prediction. And we can calculate the model accuracy by just manually do this. You just sum up those correct predictions divided by the total number of your data. So this is how you manually do it, or you can just pick the value from this matrix. See, I assigned this little table matrix as this name confusion. So I picked the diagonal value divided by the total number in this table. So this total number is actually the total number of the data points. Or another way to get the accuracy, you can just take the mean where it got correct prediction, because it's automatically sum up the total number of equals and divided by the total number of the elements in this vector. It will be like a vector of true, false, and you just count how many of them are true and divided by the total number, the length of the vector. Well, the accuracy being 0.5216, that means only 52% are predicted correct. It's not very good. It's just slightly better than a random guessing. Remember, if we just flip a coin, a fair coin, we should get 50% accuracy for a random guessing. So this is not that good. Well, actually, for stock data, we all know, or many people know about stocks. You know, it's very hard to do predictions, to modeling the stock changes. Even with time series models, the models, it's hard to do prediction. Well, that's probably why. That's why we got really bad prediction accuracy. But this is actually only for training data set. We actually want to know how the model performs on future data, where we have not seen yet for the future data. So the exercise is to train the model on 2001 to 2004 data, and then do predictions on 2005. So this is your training for this 4 years of data, and you do testing on this last year. And we will use the GLN, and it has a subset argument to do this training and testing data set. Where you first get the index for the training, when the year greater than 2005, you will decide that you're training. That's the index of the training set. And when you do the new model, you specify the subset equal to this training. This is the index that you just give to this GLM. It will recognize you will only doing the regression model, doing the modeling on this subset. And this is what you get for the model. And still, it's not a great model just by looking at the p-values for your predictors. And well, next, I did how do we get the prediction? So this is for get the predictions for testing data. And you first get the X values for this testing data, where this S market data exclude those training data index. So remember, this train is that year less than 2005. And this would exclude those rows that are having year less than 2005. And direction for the response variable do the same thing. So you get both X and Y. So this is actually the whole data set corresponding to testing data. And if you do the to do a prediction on the probabilities, and you specify the new data as this data set. So it's a data frame with all columns, but just the rows for year less than 2005. And again, this is how you get the prediction to up and down, kind of translate the probability to the actual meaning of your response. Greater than 0.5, you name it up. If it's less than 0.5, by default, you put it in down. And just change those values, having probability greater than 0.5 to up. And now if you look at the configuring matrix, configuring table, whatever, and this is what it's like. Or you can tell if we do the accuracy is getting worse. Well, as I said, this is just for illustration purpose. And actually, the book suggested maybe we can do this regression on only lab 1 and lab 2 and still use the training data, do a logistic regression, and just take a look how it does, and it tells us the accuracies actually get better. Well, I guess like they decide to use this two variable probably because they see this two having relatively small p-values. So anyway, this is what the book says. And here I kind of illustrate how to look at a confusion matrix and how to split your training and testing. How do you do that? How do you do the training, the regression on the training data, and also do predictions. And remember that the prediction will only give you the probability of y equals to 1, and you have to translate it back to the meaning of y equals to 1 and y equals to 0. Well, we'll stop here.